I think here are some examples of differential equations. Sometimes I like to classify differential equations in terms of the highest derivative that's being applied to the unknown function. Look at my very first example. Here's an example of a differential equation. It's a differential equation because it involves a derivative of an unknown function y. And it's going to be our task in the semester typically to find that function y that satisfies that differential equation. The techniques will invariably involve anti-differentiation or integration. Bottom line, we've lied to you this whole time. We told you math, you calculus 2 graduates, that, oh, integration and integrals is so wonderfully applicable, so many applications, but technically speaking, the biggest application for you guys is to be able to solve differential equations. So we're really going to put our integration skills to the task soon, this week. I will sometimes subclassify this differential equation as a first order differential equation because the highest order derivative is the first. What order differential equation is my second?
First.
It's still a first order differential equation, isn't it? Because it only involves up to a y prime, not y double prime. Now sometimes I might even subclassify differential equation in terms of being linear or nonlinear. Now, a linear differential equation is merely a differential equation in which every time you see some derivative of y is involved in the linear expression. In other words, y prime, y double prime, etc. is always raised to just the first power, not embedded in some other function. So I would subclassify the first dE as a first order linear differential equation because when I see my y and my y prime being raised to the first power, I think here too, this is a first order linear dE. It involves only first order derivative. But every time we see y prime or y, it's being raised to the first power, hence it's linear. Now, is this first order linear with what I just said? See, I think it's neither first order nor linear. It's not linear because look at the y prime is being raised to the second power. Oh, here's another reason why it's not linear, because y is embedded in the argument of a logarithmic function. I also would not classify as first order, I classify as second order because I see second derivative. So I think my third example is a second order non-linear differential equation. I think my fourth example is, I'm talking too much, I'm hearing my voice too much. My fourth example is third order.
And linear.
And linear. What about my oh, I got two number fours. I like the number 4 apparently. I'm a mathematician who can't count. Sorry. What about my fifth example? Well, it would be a fourth order because fourth order derivative, but also be non-linear because y is yet again embedded in the logarithmic function. Oh shoot! Did I make a mistake with the second example? I said it was linear. Should I have said non-linear? The answer is no, I didn't make a mistake. It doesn't matter what the heck is going on with the independent variable x. The only thing I care about in terms of subclassifying as linear is what's going on with y prime, y double prime. I still think I'm correct. This is a first order linear dE because I don't care what's going on with the variable x. If you can read that, you guys, that is an x. Jeepers. Sorry. Happy with my vocabulary so far? Oh, by the way, something else I didn't put up here as an example. Shoot. Sometimes I subclassify a dE as being an ordinary differential equation, and I use an adjective ordinary when the function for y is a function in only one variable, which is what I meant in all my examples. I meant y to be a function solely in the variable x in 5 examples. If y is a function of 2 variables, we will not deal with it this semester. That would not be an ordinary differential equation, it would be a partial differential equation. And partial differential equations is a whole new topic. You guys, I'm sure many of you will study it when you move on to the next level. So, if we're going to solve differential equations, let's talk about what it means to have a solution to a differential equation. Is this a solution to this differential equation?
Looks like it.
I shouldn't ask that question. I should ask a better question. How do I determine if that is a solution to the differential equation?
Differentiate with differentiate.
Yeah.
Yeah, let's just differentiate. How about use math D language? Let's just see if the solution satisfies the differential equation. Watch. If I assume y is this garbage here, when I plug it in for y here and here, do I get the same thing on both sides equal sign? Okay, can I rephrase that? How about being more lazy? Let's just you and I take a peek at the left-hand side of the dE, which is dy dx, and see if we get well, what you see on the right-hand side. And if I get the same darn thing, I know that solution. Excuse me. I know this function is indeed a solution to my differential equation. Let's check it. Yikes, yikes, yikes. So I'm going to differentiate with respect to x my function for y, which by the way is nothing more than c times e of kx. Let's differentiate. I think what that gives me is, I don't know, you tell me. Oh, chain rule. It says I got to multiply by the derivative inverse function with respect to x. But this is just k times c e to the kx. But this is just k times y. Oh shoot, that's the other side of my differential equation. I guess I just showed you, the reader, that indeed this is a solution. Excuse me. This up here is a solution to that differential equation. Are you there? Oh, you guys, I don't like my example. It's too yeah. So. Shoot. Hold on. Okay, now I'm getting myself into some trouble. Shoot. So in order to answer my question, do you guys not agree that what I really need to do is check out what the heck is on the left-hand side of my dE? That is to say, this mess. And see if it's, well, jibber is just equal to what's on the other side of the dE. Do you guys agree? That's the question. So, in order for me to do this, can I take a break? Can I pull out a nifty piece of scratch paper? If that's my function y, then I'll need to differentiate once and twice. So you guys allow me over here to pull out a piece of scratch paper. And I maintain if y is equal to this, you guys, am I writing this down correctly? Tell me if I'm not. What did I say? X? Sorry, 1/3. X e to 2x. If that's what y is, let's compute y prime. I said, let's compute y prime. I can say it 3 times. Guys, negative C1
e to the negative x plus 262 e to the 2x plus 2
plus
chain
2/3 x plus 1/3. Is that right? You guys tell me if I'm wrong. And y double prime is going to be c1e to the negative x plus 4c2e to the 2x plus, you guys are making me do all the work. Is that a 4/3 x plus 4/3?
Can you just quickly
Yes.
explain the first step there?
You mean from here to here?
No, from how you got from there to there.
Now, I'll be honest with you, what I
Yeah.
really did, I just copied down my y.
Okay.
And because if I had to slam this into the dE, I had to differentiate once and twice, I was just taking a break. and computing my first and second derivatives. And
Okay.
Brad, if I'm being too sloppy, look, that's a prime. I really meant that was the first derivative. So
Okay.
I merely differentiated once and twice. But now to actually answer my question, I guess I better go in and take my y double prime. You guys help me with this. Is that a c1 e to the negative x plus 4c2 e to the 2x plus, was it a 4/3 x plus 4/3? Minus my first derivative function, I misspoke, I didn't misspeak, I should say it more smoothly, minus my y prime, but isn't that a plus? c1 e to the negative x minus 2c2 e to the 2x, I forget the rest.
Yes.
Is it minus 2/3 x, is it plus 1/3? E to the 2x? Oh shoot, I missed my minus 2y. So that'd be a minus of 2c1 e to the negative x. Minus 2c2, I think, e to the 2x. Is it a minus 2/3 x e to the 2x? And in removing parentheses, collecting like terms, actually, forget about parentheses. Let's deal with e to the negative x first. Here is one of them. Here is two of them. Oh, minus 2, they're gone. As far as c2 e to the 2x terms are concerned, in red, there's 4. I said red, sorry, in black. There's 4 of them. Take away 2, there's only 2 of them. Take away 2 more, oh, they're gone. Next, when it comes to x e to the 2x terms, there's 4/3. Minus 2/3 down to 2/3. Minus 2 more thirds brings it down to 0. So I guess the only thing remaining standing are those nice clean scalars times e to the 2x. But let's check out what happens when I combine those two terms. Is that 4/3 of a minus 1/3? Is it 1/3 of, excuse me, 3/3, which is just e to the 2x. Oh, thank goodness. That's what I was supposed to get. So I guess indeed this is a solution to that differential equation. You guys, this is a lousy question. It's a lousy question because I'm asking you, is something a solution to this DE? It's a goofy question, but I'm just trying to shake you up as an introduction to differential equations. I think a much better question is this. How the heck do you solve a DE from the beginning? From scratch. That's a better question. That's going to have to wait, I don't know, maybe 4 weeks. We'll be able to solve a DE. I always feel so awkward the first day of this class, only because I feel like I'm just dumping so much vocabulary on you guys. And I hate to do that. And if some of my vocabulary is not natural, don't worry about it. You're not going to come to class any day this semester with me quizzing you or giving you an exam, testing on this vocabulary. It's just that once you and I start diving into solving differential equations, the vocabulary is just going to be second nature for you. So don't sit here in class today saying, oh my gosh, I gotta remember all these words. It's not that big of a deal. I think it's kind of goofy, but at least it's some way for me and the author test to come in and give you a quick, I don't know, I guess a keyword, introduction to differential equations. Oh no, I forgot something. Shoot. Because I already gave to you this example right here. Is that example number 7? guys are gonna make me solve this in my head again, aren't you? Was it C1 e to the negative x plus C2 e to the 2x plus, I think it's 1/3 x e to the 2x? Okay, a bit more vocabulary. Actually, scrap the vocabulary. Let's do something different. If in solving a differential equation somehow involves the anti-differentiation process, does it not seem reasonable, you guys, that when it comes to a general solution to a second-order differential equation, I should come up with maybe two constants, sort of like coming up with constant integration? After all, you take some function and anti-differentiate twice, aren't you going to come up with two constants of integration? So, in general, if I have an nth order derivative, the general solution would involve n constants. And that's why in this example, I know I'm the one who made it up out of thin air. But I think in this example, I've got two constants because this is a general solution to a second order DE. Now, what do these solutions look like? Well, actually, I shouldn't ask that question. How many solutions are here? How many solutions do I have? See, I think I've got infinitely many because I don't know what those constants C1 and C2 are. And so I think I've got a whole family of curves in the Cartesian coordinate system in the xy coordinate plane that are indeed solutions to this differential equation. However, if I give you some kind of constraint like y of 0 equals 1 and y prime of 0 equals something else, then I think that's going to allow me to find one particular solution to the differential equation. I think this is enough information to allow me to find these constants C1 and C2. Sometimes when I give you this criteria like this, I sometimes refer to this as an initial value problem. So an initial value problem simply is a differential equation with a certain number of conditions that correspond to the order of your differential equation. Now, in this example, is this really enough information to find values for C1 and C2 in this example? I think the answer is clearly yes. Using that first criteria, that y of 0 is equal to 1, I'm simply going to take my solution, this right here, my general solution, and plug 0 for x, and 1 in for y. And if I do that, I think I generate this equation. Actually, you tell me what I generate. Is that a C1 plus C2 being equal to 1? But my second condition tells me that negative C1 plus 2C2 Anybody? Want to finish this? So you said plus 1/3. Where'd you get that? Yeah, you guys cheat. Look over there to the left. I think on the left ink board, I've already got y prime already computed for you. So if I plug 0 for x, is it not true that I generate another term on the left-hand side, namely positive 1/3? And this is going to be equal to positive. You guys help me with this. Does we see where I generated these two equations? They simply came from these two constraints. So yes or no? Is it a piece of cake to solve for C1 and C2? Yeah, it's a MAPD question, isn't it? Now, adding these two equations together, I see that C2 is equal to, I don't know. I really don't. Is it? I came up with 8 nines.
Yep.
Am I wrong?
It's it.
Is 8 nines? Okay, thank you. And now to find C1, oh, just plug that back in for C2 in the first equation. I see C1 clearly is equal to 1/9. That being the case, my particular solution is going to be nothing more than y being equal to my particular C1 plus my particular C2 times e to the 2x plus all the other garbage in there. There is one single solution that is indeed a solution to this differential equation given this particular criteria. Are you there? I got an idea. Let's change this. Can you still do it? Yeah, I think we can still do it. I think the algebra is the same. It's just my numbers might be a little more complex. After all, when I substitute 1n for x and simultaneously 1n for y, let's rewrite that equation. I think that becomes c1 times e to the negative 1 plus c2 times e squared, yikes, plus 1/3 e to the second is equal to 1. But now plugging 1n for x and 2n for y prime in the second equation, I think that generates negative c1 e to the negative 1 plus 2c2 e squared plus I don't know the rest. Is that a e to the 2? Do you guys mind if I stop? Yes or no? Is that a piece of cake to solve c1, c2? Hoping you say yes, please. Okay. But if you want to solve it, I'll solve it. It's up to you. Is that okay, Alex?
No, I was trying to figure out how to keep my iPod silent when I take pictures of the whiteboard.
Oh, gotcha. It automatically makes a sound.
It always makes that shutter sound.
I don't
It's
care.
a legal thing, so that people can't take pictures of people who don't have.
No, I managed to turn it off.
Did you really?
Yes.
Oh, never mind.
Yeah, I'm surprised it doesn't have something in the setting. But anyway,
This
Alex.
was just me going, yes, I did it.
Gotcha. Actually, you guys, can I restate this? Can I make this more official? I think I talked about an initial value problem in terms of a specific example. Let's generalize this. An nth order differential equation. With the following conditions. Namely that y vat is some value of x, call it, you guys, I'm making these symbols up out of thin air, call it x sub naught, is equal to, I don't know, how about y sub naught? And what about y prime evat of x sub naught is equal to something else, I'll call it y sub 1, all the way down to an nth equation, which would involve the n minus first derivative for y evaluated something, call it x sub naught, is equal to something else. How about y sub n minus 1? It's called an initial value problem. I just think my examples numbers 7 and 8, or excuse me, I misspoke. I meant numbers 8 and 9 were merely examples of second order DE with two conditions. But it could have been nth order DE. I just have to have n equations in order to establish that I do indeed have an initial value problem. You guys, I'm stalling. I'm stalling because what else do I need to say to introduce you guys this whole concept of differential equations? Talked about solutions. Talked about initial value problem. Do not take this the wrong way. I have not told you how to solve a differential equation. Gotta confess, to wrap things up, I suppose I could have. Do you guys think you can solve this differential equation? Do you think you can write a differential equation that represents this physical phenomenon? Actually, this is a rhetorical question. I've asked this before in Math 30. I know somebody from Math 30. I know you can answer this question. Guys. Well, do this for me. What can you say about the acceleration of this object due to the gravitational pull for any planet?
Constant.
Yeah, it's just a constant. Can I give it a name? Can I call it G? Actually, since my initial goes in the upward direction, can I call it negative G, so the G is a positive number? You can call it positive, that's fine. It doesn't matter what direction you really want to orient. I'll just be consistent. You guys, look at that. That, I think, is a differential equation. Because the second order derivative for the height function, and I think that second derivative is nothing more than a constant. Now, I gotta confess, I have not answered my question, which is find H. Did I not write the question? Sorry. Find that function H. We can solve this DE. It's a piece of cake, because I'm just gonna anti-differentiate. And I think I'm left with H double prime be equal to negative G times T. Thank you, plus a constant of integration. Yes, I'm sorry.
Is it H double prime or?
My apologies, I misspoke. I said let's anti-differentiate, that'll give me H prime, correct? Not H double. Oh, by the way, I think I goofed up on somewhere else as well. I may not have made a mistake. I don't like using the C1 garbage, so can we take a quick break? Where? I think H prime is nothing more than representing the velocity of this particular object at time t, and I know initially I got a velocity of v sub naught. In other words, H prime divided at 0 is equal to v sub naught. So when I plug v sub naught in for H prime, and I plug 0 for t, I think this is what I get. Meaning, of course, whoops, that my C1 is equal to my v sub naught. Okay, can I rewrite? I guess what that really tells me is that H's derivative is negative G times T plus my C sub 1, which I just found to be V sub naught. Shoot, I still didn't answer my darn question. I wanted to find H, so let me anti-differentiate one last time. And I think H as a function time t is going to be negative 1 gt squared plus V sub naught times t plus, oh shoot, another constant integration. Where? It's also the case that I was indicating that the initial height was going to be H sub naught. So when I plug H sub naught in for H and 0 for T simultaneously, I think that's going to tell me that my C sub 2 is going to be nothing more than, did I say C sub 1 again? You guys, this is another mistake on my part, isn't it? These constants aren't necessarily the same, are they? My apologies. I meant C2. I think it simply tells me C2 is thank you. Plug it in. I guess my height. So function time t is negative 1/2 times g, the acceleration due to the gravitational pull of this particular planet, which by the way is
9.8 meters per second.
approximately 9.8 meters per second, or
32 feet.
approximately 32 feet per second squared. T squared plus my v sub naught t plus my C2, which I just found to be H sub naught. Are you happy? Any questions? Shoot. That was a lousy example because I just wasted your time. That was simply a Math 30 question. Maybe the questions I have this semester will be much more sophisticated in terms of solving more complex differential equations. We'll get there. It's just going to take a little bit of time. Guys, give us some feedback. You look just dead. Is this just so easy it's boring to death, which is good? Is this killing you, or you just want to think about it? Give me a show of thumbs. Okay. Wow. I expected this. I see a lot of this. Awesome. Do you guys think for our first day, can I stop talking math? Can I take care of some administrative business to finish up today? Okay. So in taking care of my administrative business, here's what I need. So, nobody's older than me, so I guess that wouldn't be too embarrassing. Shoot, where am I at?